Have the third lecture, Michel Brion. Michel. Okay, thank you. See what happens next. Well, anyway, I'll try to explain some topics on crop strings. Wonderful varieties. Monoids. Okay, so crop strings is kind of universal construction. It starts with say projective algebraic geometry and produces some universal coordinate ring. So you see, if you have a projective subvariety of this space, you have the homogeneous coordinate ring, but the crop string puts this ring together into a universal one. So I will give the definition in a moment, but I will be mostly interested in this talk in wonderful varieties. So I'll set up some notation first. So G will be a semi-simple, simply connected group. The thing will be over C. X will be a wonderful G variety. As in yesterday's talk. And we will fix a Borel subgroup inside E, as usual. So simply connected is not a big restriction, and also semi-simple, because for a wonderful variety under G, it's easy to see that the radical of G, the large central source, acts trivially. So you can just kill the radical and go to the semi-simple part of G, and then you can take the simply connected cover. The use I will have with this assumption in the talk is that every line bundle on X has a unique linearization. So let me write it. Every line bundle L over X has a unique linearization. So this means that you can lift the action of G on X to an action of L, which sends each fiber linearly to another fiber. And so in particular, G acts on the space of sections. And this will be very convenient. Usually it's not completely true if you start with an arbitrary G. Okay, so
this is an assumption, right?
Yes. This is a consequence of the fact that G is simply connected. Okay. Okay.
X needs to be normal. X needs to be normal.
A wonderful G variety is smooth, so I'm safe. But you're right. In general, X needs to be normal to have this existence. Okay, thank you. Okay, so let me first describe the Picard group of X. I claim that this has a canonical basis. These DIs are the irreducible stable divisor. Which are not G stable. So this is not hard to see because actually, if you take these divisors and remove them, what you obtain is exactly the image of the local structure of Führen that I mentioned yesterday and the day before, which is a kind of cell. So you have this parabolic subgroup P and a kind of slice, which was CR. And this is an open subset of X, which is abstractly isomorphic to an affine space, because this is an affine space, another one. And it's easy to see if you have an affine open subspace, affine space as an open subset, and then you get this. Another fact which is worth mentioning is that these DIs are base point free. Let me explain why, because I think this relates with something I mentioned earlier. So since DI is B-stable, you have a canonical section. Okay, that's a canonical section of a divisor. And as I mentioned, there's a G action on X, which is unique. And this DI should be an eigenvector of the Borel subgroup, because its zero set is B-stable. With some weight, which I will denote by omega I. That's just a definition of the weight. It will be related with fundamental weights in some examples, so the notation at least makes sense, but it's usually not a fundamental weight. Okay, so we get this special sections with base locus DI, and then we can take their translates, and their translates are base point free because this divisor actually doesn't contain any orbit. For the G S DI, have no community. Okay, so and in fact, this DI generates monoid of base point free divisors, which is the same as NEF divisors. This is completely similar to the case of projective varieties I started with. And it's for basically the same reason. Okay, so that's for the Picard group, and now I can define the Cox ring. It makes sense whenever you have a 3D generated Picard group. You just take the following thing. Take the sum of sections of all possible line bundles or divisors. So let me write it formally. The sum will be over all integers. Positive or negative. So I just take all possible sections. And you see, this is graded by Px, dm. And it's also a ring because you can multiply these objects. And that's why I have to more or less choose the basis of the Picard group. Otherwise, if I take some of our isomorphism classes of Langlands, I would be in trouble for multiplying. But here I can do that. So this. Okay. So that's a general definition, and it comes with a diagram. Let me write X tilde for the spec of this thing. And well, another thing I should say is there is a G action on this, which commutes with which preserves the grading. So on this X tilde, you have an action of by the same reason. You have an action of the torus with character group Px. This torus I will denote by Sx. Fine. Let's see start with the end. Okay. And we have a diagram where the other ingredient is a relative spectrum. So this should be the spec of over X of the corresponding sheaf. So I take this sum. So this is just a sheaf of algebras over X. And so I get a diagram like this. So you have X hat defined over X. And it's mapped to X tilde, which is the spec of A of hat. Okay, by just nonsense. Okay. So this is the affinization map. Okay, I will write it with an for some reason it will be clear. So let's collect what we can say about this diagram. So first of all, Q is a G equivariant, and it's a massive process. Well, this is just a variant of the construction of a C-star bundle associated with the alignment. Okay. You just put it with n copies, so it's not a deep fact, but it's a nice fact. And actually, it's called the universal also. It was used in arithmetic geometry before the coxswain was invented somehow. So that's a very nice tool somehow. Now, what can be showed is that this coxswain is UFD. I will give a reason for this tool, and it's also finitely generated. These properties are special to this situation. In general, the Cox construction produces something, but it has no reason to be finitely generated. But the reason is, if you look at this X hat, yes, here, this is a smooth spherical variety for this group action. And this is, I guess, quite obvious. First of all, it's smooth. Okay, I will not speak to this. And you see, X is a spherical variety, so there is an open orbit of B, and above it you have an open orbit of B times Sx. And now it's a kind of nice exercise to show that the coordinate ring of any spherical variety is always finitely generated, even if the variety is not affine or whatever, because it's a multiplicity-free sum of representations, and the weights which appear are in some finitely generated convex cone. So you get, you see how to complete this argument, or you ask me for details. So it's not a big deal. And so that's the main input. Since this X tilde is a spectre of O of X hat, you get this.
Can it follow also from the fact that it's log Fano, that X is log Fano?
Possibly, but you don't use. I think this fact that coordinate ring of spherical varieties are finitely generated is also useful in for other reasons. For example, it tells you that these things are Mori dream spaces, That's good to know. Okay. So whatever you start with. Okay. UFD. Let me explain with hands, with some hand waving. So you want to show, well, maybe I should say an additional thing, which you must forget that I is an open notion. And the image is a big open subset. Means the complement of the image has codimension at least 2. Okay, so this is a general fact for Cox rings. Once you know that they are finitely generated, it's a formal consequence of this affinization business. Okay, so I will use it because, for example, to show that Cox X is a UFD, I have to show that every divisor on X tilde is principal. But by this fact, it's enough to show it on X hat. And on X, I know what the divisors are. So there are inner combinations of this. So let me take an effective divisor here. And let's pull back. So here I have a canonical section of this divisor. And if I lift it here, I get a regular function. That's why the Cox ring is made. And this regular function has 4 zeros exactly this one. And that's basically the proof that divisors are principal. Also, divisors are pullbacks of divisors downstairs because up to linear equivalence because this is a principal bundle. Okay, so that's very quick sketch, but I hope it's easy to fill details. You go to a very nice book on Cox rings for all person can find them. So now the main observation on this Cox ring is the proposition. But if you look at this Cox ring and take the U invariance, U is a unipotent part of B. What you get is a polynomial ring in the variables S, D, I, which are the canonical sections of the divisors D, I, and the canonical sections of the boundary divisors. So let me recall what they are. Maybe I should have put them here. Sorry, I will find it for a minute. So I will consider the boundary of this, and it's of this form, well, xi are irreducible, least stable divisors. Okay. So that's well, it's not difficult to prove this, but it's very useful, and it's an analog of the theorem of Cox, which, as the name suggests, has some relation with the Cox ring. And you showed that if you start with the toric variety, then the Cox ring of X is the polynomial ring generated by the sections of the boundary divisors. There are many of them. So these are the irreducible components of the toric boundary, and they freely generate the Cox ring. Later, there was a converse. If the Cox ring of something is a polynomial ring, then this thing is a toric variety. By Okay, so maybe I will not prove this proposition, but again, the proof is not deep, but it has some nice consequences that I will explain. Especially if you reformulate it in a geometric way. This looks like a very algebraic statement. Maybe you don't see, it's not clear what it should mean, but it has some nice consequences. So the first one is, first of all, if you look at the G invariance, instead of U invariance, then you get polynomial ring in the sections of boundary devices. Because, the others are B eigenvectors of some kind of positive weight. So this, and the other thing which is quite remarkable is Cox ring is a free module over its ring of invariance. Okay, which is quite nice fact. Well, the proof is extremely short. Well, for the invariance, you get it, and for this freeness, well, you cook up this free module just by looking at the other generators. And let's define some space. And maybe I define it as M, which will be the span of the G translates of the monomials in the other divisors. There's one. So this is a G submodule of Cox X, and the claim is the map from this tensor product to Cox X, which is that's a multiplication map. Is another isomorphism. The proof is also almost no proof, because you have a morphism of representations of G, because everything is a G module. And if you go to the U invariance, well, you just replace these G modules by this monomials, and you get an isomorphism by this theorem. And so by highest weight theory, this is an isomorphism. So this is just representation theory. Okay, so that's was some algebraic reformulation, but there's a maybe more appealing geometric one, which says so let's just consider the GIT quotient by G of this X tilde, which is a spectrum of the Cox ring. I call it maybe F, not such a great notation, but I will use it. Well, first of all, this one is C to the R because of the corollary. This one is spectrum of a polynomial ring, and F is flat. It's normal irreducible fibers. Okay, well, that's the statement. And so flatness is just what we observed in a stronger sense. And normal irreducible fibers actually comes from a statement in for varieties with action of a reductive group. So if you have a fine V spin Z, you can consider its coordinate ring and the U invariance. And the fact is, you can read many geometric informations on Z on this coordinate ring. So this one, for example, if this one is normal, then U of Z is normal. And same for integral or reduced. And if you apply this observation to this, you observe also that for the fibers of this map, what you get as O of ZU is the polynomial ring in the SDI. And you get this statement. But it's not a deep fact. And for the proof of this kind of statement is, again, higher straight theory, sometimes in a more elaborate way, but it's not very difficult thing. Okay, so we get this picture of X tilde as a kind of vibration over CR. Well, of course, it's in the setting of affine geometry and not at all proper. But you see, if you have this GIT quotient, you should think of it as a proper map because it takes closed G-stable subsets to closed subsets. So it's closed as regards G-stable subsets. And that's what maybe you should keep in mind to understand the geometry of this. So let me try to say some additional information on the fibers of this map. So first of all, this map is equivariant with respect to the action of Sx, this torus we had. And actually, we will not need the full action of Sx, but a kind of sub-action, which I will introduce next. So first of all, there is a map from this lattice Zm to the weight lattice of T. This was my notation for the weight lattice of T. And it sends the class of Vi, to the weight omega I. Okay, but just taking the weight associated with these devices. And this is a homomorphism of lattices. So in terms of tori, you get a map in the opposite direction, as you know. This gives a map from T to Sx. And instead of looking at the action of Sx on all these objects, I will look at the action of T. Well, one main point of this map is it's not a trivial fact, but it sends this xj to the spherical roots. Okay, and that's another way to understand this spherical roots. And so you see that this map F is T equivariant, where T acts on CR via the spherical roots. Okay, and that's, yes?
Sorry, I'm confused. Wouldn't these be G invariant associated to the XJs?
Yes, but not in terms of weights, because to compute the weight, you have to express xj in terms of the di's. And what you do for this is restrict to the open part, and then you get this weight. If they went to 0, then this xj would be triggered. Okay.
No, I was getting confused with the whole to go to negative.
Negative. I think this is correct because well, it's tricky, but I double check it, and I don't swear it's correct, but I double check it, and the idea is this xj and di generates effective cone of effective divisors, and this cone is a cone of roots, and it contains the dominant chamber. Okay, otherwise you get something.
Okay, so these WI, sorry, these omega i's are like the fundamental weights for the gamma case or something like that?
Not always. But that's a good way to think of them, but it's not always true. It's more complicated. For the group case, you get this relation, which I will give in detail. In general, even for symmetric spaces, it's a bit more complicated. So, but there is a kind of Cartan matrix, but it's not a definition. It's not universal truth. Okay, anyway, you have this geometry. And so you see that for fibers, using this action, I can always bring some point to coordinates 1 or 0. So the consequence of this discussion is that fibers of F at some point x1 R only depends on the set of non-zero coordinates. So there is a general fiber which will be at 1, 1, 1. And the fact is, it's closely related with orthotropy group H of the open orbit, but not exactly this. So it's the spec of O of G mod H1, where H1 is the intersection of all kernels of the kernels of all characters. So that's how it is. So it's a bit more complicated than one you would expect, but we will see in an example that you really need this H1 and not this H we started with. So of course, G mod H is the open orbit index. So in other words, you have H1. H mod H1 is diagonalizable. And H1 is a smaller structure. This is problem. Okay, so that's a general fiber. For the most special fiber, which is a fiber of 0. The result is it's spherical. In the following sense that this fiber x tilde 0 is G translates of its U invariance. And this
Excuse me, there. What was H?
G mod H is the open orbit in X. Sorry, I should have written it in the general conventions.
Okay.
And H1 is just slightly smaller.
So what would be the open orbit in X tilde?
Sorry?
The open, what would be, I mean, X tilde is also a spherical variety and an embedding for any open orbit. I mean, what would be?
Let me write it here. So the open orbit is an open orbit for this C star to the M. Okay. You have this group action, and you divide by the H action. H is, as we just said, H is mapped to G, as you know. And then to map it to C star to the M, we need M characters. These are the weights of this DI. So this DI live in X, but actually they are uniquely determined with intersection with G mod H because they are not contained there. So you get divisors in G mod H, and you can lift them to divisors of G. And since G is simply connected, its coordinate ring is UFD. So there is a global equation for this DI hat. And this global equation is a eigenvector of B to the left with weight omega I, and H to the right with some weight chi I with respect to B times H. And this chi I gives you this characters that are needed here. Okay, so that's a kind of formal stuff. Yes.
That homogeneous space has a, say, semi-simple part. That would be G mod H or G mod H1, or?
It's G mod H1. Right. If you divide by C star, you get exactly G mod H1 because this key I, they generate the character group of H. So the intersection of the kernels is exactly this H1. Okay. That was part of the things I wanted to hide, but okay, it was not successful. Okay. Really, no, because there are lots of algebra behind this. And, it's interesting, but it takes some time. Maybe I still give you more algebra because I think it's related to maybe I put it here. So to prove this, we need an algebraic description of the Cox ring, which I will just sketch. And actually, the Cox ring embeds in the coordinate ring of G times T. Okay. Well, I will explain exactly how. And this ring you can see as a direct sum of coordinate ring of G times characters of, for reasons, I put these characters in exponential notation. So this will be the sum over all weights of this times character. Okay. And then I can describe the Cox ring. It's a kind of twisted sum. This is a direct sum over all lambda and mu. Let me write it and explain the notation afterwards. So the condition is lambda is smaller than mu, so lambda would be a dominant weight, and mu is a bigger weight. And here I put O of G, EU, and I will add some condition on this part. This should be H1 invariant and isotypic of weight lambda. So I hope you can see this. And let me try to explain all the messy ingredients of this algebraic description. So first of all, this is clearly a subsum. Here I take H1 invariance, that's this notation. I take isotypic components of type lambda, so the sum of all copies of V lambda acting on the left action. And then I should explain this order. So this means that mu minus lambda is a sum of spherical roots with positive coefficients. So probably you are familiar with an order of the weights of some simple group where the positive elements are sums of roots. And here we just take sums of positive roots, of spherical roots, which are some special sums of roots. Okay. So that's a full definition. Well, it's a kind of heavy description, but still you can see how things multiply in this ring, because you multiply there, and in O of G, the multiplication is rather well understood. Simple modules multiply according to their tensor products for character reasons. Okay, so you have some grasp on the multiplication here. That's what I want to say. And out of this, you can describe this violence.
Okay. So is mu also in lambda plus or
no? No, because no, this mu can go to arbitrarily high. And well, I should explain in this description, well, maybe I don't have enough room for this. What are these sections? Because in this Cox ring, you have a special elements, which are these sections of DI and SJs. And the section of XJs are just correspond to E to the gamma J. So that's a simple description. And the section of DI, they correspond to something in O3, F, DI, E to the omega. This is equation of this feedback. Okay.
You mean they correspond under the
isomorphism? You have some isomorphism, which I didn't explain, so with a formal sign. And then these sections go to these elements. And then you can multiply and get higher coefficients. So that's a picture. And well, it has the merit of being effective. Okay, so at this point, I should give the basic example of this theory because it looks very heavy, but I hope you'll see more on this example, including this mysterious isomorphism here. So I would like to present the example of the wonderful compactification of the adjoint group. But then this will be a bit tedious because I started with a simply connected group. So now the group is G, which is G is correct. And it has a wonderful compactification because it's a point. And now the group which acts is G times G. And it's not the original G. So we have to adapt the notation to this double setting. So we need a Borel subgroup, which will be something like B minus 10 times B. Well, B and B minus are opposite Borels. It's for convenience reason. We need a maximal torus, which will be T times T. And now this DIs, well, they live in X, but I can pull them back to G. Maybe I prefer that for them. And this will be E minus S I. These are the simple reflections. Because if I did things correctly, these are exactly the B minus times B orbit closures of codimension 1. Yeah. That's why B minus is easier because I don't have to fit by W naught or whatever. Okay, so we get this. Now this weights omega I, they are double weights, and this will be minus I fundamental weight and I fundamental weight. Okay. Again, by this convention. And the spherical roots, gamma I, this will be, then is a J, this will be minus alpha J. Okay. So things fit at this point. Now, I need this subgroup H inside D and G now. This is the isotropic group of the open orbit. And now you have to look because I work modulo the center. So this H will be Z times Z times the diagonal of G. If we, because it's a pullback of the diagonal in Giad. So we have to do this. And abstractly, it's Z times G. We only need one copy of G, the other one is get the diagonal with KZ. And so this subgroup H1, which is a kernel of characters, this is just G. Okay, so that's why you have to take care of all this space. So, well, sorry, abstractly the diagonal. So you see the general fiber is of F, which goes from tilde to round. You get and special fiber. This needs some checking. You get reflection of something which is O of E times G modulo U minus U. This is the kind of limit of G in the sense of group. Okay. And now this X tilde now you see that cot X is generated by at the ring by S1 S R these sections of mine, and also this G times G times S I. I goes again to 1 R. R is the rank of G. If you translate this geometrically, you get that X tilde sits in CR. This is CR associated with this section times the product of endomorphisms of V omega I. Okay, so that's the way it's built. And it's very easy to imagine how it sits. It's an orbit closure. Of when you take 1, 1, this calculus, and then you get identity in each V omega I. And I have to say under which group? Under V times G times T. The T acts so it acts with X. So the first ones are the spherical roots, the simple roots, sorry. And second ones are fundamental roots. And well, put the correct notation of this. Okay. So that's a rather explicit description. And, what you see from this is this is an algebraic monoid. It has a composition law that by pointwise multiplication and composition of endomorphisms. And this X tilde is a submonoid because the action here preserves this monoid. So this is the monoid. And it's easy to see its unit group. Well, you get G times T divided by the center, which is embedded simultaneously in both. That's easy to see. And this is called the Vinberg monoid. Okay. Well, Vinberg called it enveloping. And Vinberg constructed it backwards because he wanted to construct the wonderful compactification of G-ad in a purely affine way by affine geometry. So he defined this object, and he said inside this there is an open subset, which is our X hat that we started with, this relative spectrum. And from X hat, you get the principal bundle to X, and that's what was how he got this X. So we just played it in the opposite direction. Okay, and there is another object which shows up in this picture. This is a special fiber. It's called by Vinberg the asymptotic semi-groove. And it's a semi-groove because you have a monoid, and the projection to the first factor CR is the homomorphism of monoid. So the fiber at 0 is that's a semi-groove. Okay. So it has a multiplicative structure, but no unit. The unit is in G, in the open part. Okay, and that's a very natural degeneration of the group, where you just start with a multiplication of the group, and now you kind of kill terms. So now that's the general picture, and you see now for every wonderful variety, you have a similar story. But there are many things which get well, less explicit. To make things more explicit, one would have to solve a completely algebraic problem, which is can be stated as follows. And I describe multiplication. And maybe this ring that I introduced, okay? And the problem is specifically as follows. You take two irreducible sub-representations. Then by the multiplication, you can map this to this is the multiplication. And, you want to say something on the image. And, what you can say is the image contains this representation because you multiply highest weight vectors, you get some new highest weight vector, which is non-zero, plus lower terms. Lower in the sense of order with roots, actually with spherical root. And these lower terms are very mysterious, even for the case where you start with a symmetric space. And the only transparent case is in O of G, which I mentioned, but with action of G times G on both sides, because here things are double. So what you look at are something like mg of lambda for the G times G action. This is G lambda star of lambda. This sits in O of G by matrix coefficients. Right? So basic representation theory, and the claim is that NV lambda times NV mu, this times is in O of B, is the direct sum of NV mu for all mu, such that V mu occurs in the tensor product. Okay, so this is a very simple observation, and the reason is one line. So certainly you have an inclusion, because if you multiply these objects, they multiply at most like the tensor product. And to get this, you observe that inside this you have the characters, which are the diagonal G invariant functions. If you multiply two characters, you get the character of the tensor product, and so every component of values. That's the proof. So for symmetric spaces, you should replace characters with spherical functions, and the multiplication of spherical functions is a combinatorial maybe mess, open question. Except for very special classes of spherical functions, you don't know how to multiply them. The main problem for making these objects more explicit. So, sorry, I'm over time. I think I should mention just one open question, because you see in this picture, let me remind you, you have this family, which is a family of normal irreducible G varieties. And the question is whether this family is universal. And there is a theorem by, I think, Alexeyev and myself, saying there is a universal family of varieties. The point is the fibers Z satisfies O of Z has a fixed decomposition as a representation. Okay, so you look at this moduli problem, families of V varieties, which are all fine, such that the coordinate twin has a specific decomposition. And the statement is there is a fine moduli space for this moduli problem, which is an affine scheme of finite type with a T action. And that's all you know about this. And now we have one part of this affine scheme, which is CR. And, the question is whether this is a full moduli space. And, this is true for many examples, including the group case, but it's open. And maybe I should stop. Thank you.
Questions?
So I didn't really understand why it would be interesting to describe the multiplication in this ring, and what would we get from there?
Well, because one would like really to understand the Cox ring as an algebra. For example, for toric varieties, it's very straightforward. For example, finding defining relations for this embedded is based on the knowledge of the multiplication, right? So it's a generally open question to find the relations in the Cox ring. You have well-defined generators, which are minimal ones, but the relations are completely mysterious. Unless you know something of the multiplication, you cannot start, right? Actually, you need partial information, but anyway.
But like in the case of the Vinberg monoid, you always have this universal kind of thing, right?
Yes.
Yes. You need to make it more explicit or something, or the multiplication. Or what is? Yes, I'm also confused about that.
Oh, maybe. Well, sorry, I didn't express myself in a clear way. So you have a natural embedding of the Cox ring, or natural generators for the string. The question is find the idea of relations. For projective homogeneous spaces, it's a very nice theorem, but these relations are all quadratic and can be described in terms of representation theory. You look at this multiplication map from V lambda tensor V mu, and you kill all these lower terms. This generates in the quadratic relations. This generates the relations. So one would like something like that for Cox rings, but then some important information is missing. So, okay.
Questions? So the ring of invariance of Cox of X, you said, is generated by the isomers X trace.
Yes.
Do we know whether the full Cox ring is finite over this polynomial ring? Or?
No, cannot be, because if it were finite over some U invariant subring, it would be completely U invariant also. Okay, so this U invariance make a much smaller ring, but which contains somehow lots of geometric information. So that's and you see it again for say flag varieties. If you look at the Cox ring of flag varieties, a big ring. If you look at the U invariance, it's a polynomial ring in one value. Very small one, right? So that's how it is.
Okay, so there are no more questions. Oh,
I don't know what question. Sorry. So you describe also the quotient of the Cox ring by the invariant ring by the unipotent. So if you did that for the Vinberg monoid, so for the Cox ring of the wonderful compactification of the joint group, you could get like the ring generated by the roots and by the dominant fundamental weights. So that rather looks like the ring not of U invariants, but of invariants by the adjoint action of G, right?
Sorry, there are several rings. And,
I mean,
I should not lose my way with this thing. So there are rings of invariance for the algebraic actions. These are the spherical roots. Spherical. And then there is also this ring of highest weight vectors. This is this U invariant ring. Okay, that's which is much larger. And they have some hidden grading, as you saw in this talk, that you should also remember on that. I also lose my way with that. That's how it is.
The tissue invariance more or less is just closure of G module. Maybe with times the toric. The G module bar, you more or less obtain the invariance and the Vinberg monoid.
It's a bit what you get in this. I'm not sure what you. I understand this, or maybe we should discuss this. Yeah, maybe a bit later. Otherwise, during the program. So let's thank Michel for this wonderful series of lecture.